Okay, hello everyone. Okay, now I will teach about group 17. Okay, in group 17, okay, I will teach the first thing is about physical properties. Okay, and then the chemical properties, okay, involved of this. Alright. Okay, and then important uses of halogen, which is for the physical properties, I will explain about variation in the volatility and intensity of the element. Okay, and then I will add some more about electron affinity. Okay, electron affinity. Okay, and bond energy. Okay, and bond. Okay, energy. Okay, group 14 is consists of 5 elements. Okay, which are fluorine, bromine, iodine, and astatine. If you can see that when going down the group, the size of the group 17, which is halogen, okay, are increasing. Alright, and the most important thing, okay, for group 17, okay, this is the only group in periodic table, alright, which contain elements with all three states of matter, alright, which is solid, liquid, and gas is all in the same group, alright, which is for fluorine and chlorine. Okay, these both, okay, are gases state. Okay, bromine is a liquid state. Okay, while iodine and astatine are in a solid state. Alright. Okay, according to this group 17, you can see that astatine is the largest size of halogen. Okay, but okay, for the last element of group 17, which is this astatine, okay, this is the rarest element. Okay, which is it have the short half-life. Okay, half-life. Okay, which is for astatine isotope of astatine 219. Okay, its half-life is only 56 seconds. Okay, 56 seconds only. So that's why this astatine is the rarest element. Okay. Okay, for halogen, okay, its valence electronic configuration, okay, is NS2 and P5, which is located in a P block. Alright, okay, and then, okay, for elemental forms, okay, these halogens, okay, are exist as a simple diatomic molecule. Alright, okay. For all the halogen group, which is exists as a fluorine molecule, chlorine molecule, bromine molecule, and iodine molecule. So it exists as a diatomic molecule. Okay, for the first thing, okay, I will explain about color intensity of group 17. Right now, okay, group 17, okay, which is consists of fluorine, chlorine, bromine, iodine, and astatine. Alright, when we going down the group, you can see that the size getting increasing. Right, okay, hence for color intensity of group 17 element, alright, increases on going down the group. Okay, so now we can see that the color of halogen, okay, either in gaseous state, okay, or in water and in carbon tetrachloride. Alright, okay, for chlorine, bromine, and iodine. Okay, for chlorine, okay, in gaseous state, okay, the color of this halogen is greenish yellow. Okay, while for bromine is a reddish brown color, and for iodine is a purple. Alright, so you can see that when going down the group, the color become higher intensity. Okay, and then in water, okay, you can see that for chlorine, it is a pale yellow green. Alright, and some chemists said that it almost colorless. Okay, this color is almost colorless. Alright, and then for bromine, okay, the color in water is reddish brown. Same goes to in a gaseous state. Okay, while for iodine, Okay, the color is brownish orange. Okay, so it's more darkened when going down the group. Okay, hence in carbon tetrachloride, the halogen color of chlorine is same as in a water, which is pale yellow, green, and it's almost colorless. Okay, while for bromine, okay, the color same as in water and in a gaseous state, okay, which is reddish brown. Okay, while for iodine, the color in a carbon tetrachloride is violet. Okay, for the first physical properties that I want to explain is volatility. Okay, for volatility factors, okay, when we talk about volatility, you must relate it with melting point, okay, and boiling, okay, point of the molecule. Alright, so here is the diatomic molecule of halogen, which is from fluorine molecule, okay, into the iodine molecule. And if you can see that the size are getting increasing, okay, when going down the group. Okay, for the melting point and boiling point, okay, that I already explained to you before. Okay, we must refer to the structure and bonding, okay, which is, it is a non-metal, okay, and it is a covalent compound. Okay, it's a covalent compound which consists of, okay, what is the structure of halogen? Okay, it is a simple covalent structure, right? Covalent structure. Alright, so because of the all of the group 17 have the same structure and bonding, okay, hence we must compare, okay, the melting point and boiling point in terms of intermolecular forces, okay, which is weak van der Waals forces. Right? Right. So we must differentiate, okay, according to the intermolecular forces of molecule. Alright. But now, alright. So how to differentiate, okay, the intermolecular forces of each molecule? Okay. Hence, we must refer to the size of molecule. And if you can see that when going down the group, the size are getting increasing. Hence, when we go down the group, alright, the weak van der Waals forces, okay, become stronger, okay, because of the larger size when going down the group. How about the melting point and boiling point when going down the group? Alright, so, okay, melting point, okay, and boiling point of molecule are increasing when going down the group. Or we refer to the chem book, okay, thus the volatility of halogen decreasing, okay, since the increasing of melting and boiling point, okay, and the intermolecular forces of attraction, which is weak van der Waals forces, okay, weak van der Waals forces, okay, become more stronger. Alright, okay. Okay, the second physical properties is electron affinity. Okay, we already learned in the first chapter about this properties. Alright, so what is the electron affinity? Alright, this energy released when 1 mole of gaseous atom receive an electron. Okay, receive an electron. So the electron affinity is referred to the receiving an electron to form uni-negative ion under standard condition. So when we talk about electron affinity, it is about receive an electron. Alright, for the halogen, it will receive an electron to form ion. Alright, So this electron affinity is actually, alright, it's measure the force of attraction between nucleus and the added electron. Okay, which is the stronger the attraction, the more exothermic the reaction. Alright, now in explaining the electron affinity, I want to show you some analogy. Okay, some analogy. So here, okay, this is the analogy. Okay, in receive the electron. Okay, this is the receiving electron. So you can see that here is represent the nucleus. Okay, which is this is the mother. The mother act as a nuclear charge. Okay, while this is the added electron. Okay, so this daughter is a added electron. So you can see here that when the smaller size of atom, so it have higher effective nuclear charge, which is it will have higher affinity, okay, for the added electron. Okay, which is the electron affinity, okay, of this atom increasing, which is more exothermic because of the stronger attraction force between nucleus and the added electron. Okay, one for this situation, okay, you have the larger size, which is make the effective nuclear charge being lower. So the attraction force between nucleus, okay, and the added electron, okay, become weaker. Alright, hence they have less exothermic, which is less energy is being released, okay, because they have a boundary, okay, between them. Okay, a boundary lah, extra shell between them. So the attraction force between nucleus and the added electron become weaker. Alright. So the smaller size with higher nuclear charge cause the attraction force between nucleus and the added electron become stronger. Okay, hence the more exothermic. Alright, the more energy is being released because of the stronger attraction force. Okay, while for the larger size, so the effective nuclear charge become smaller. Okay, become lower. Okay, and then the attraction force between nucleus and the added electron become weaker lah. So that's why for the larger size it's not readily to receive, okay, an electron. So less energy is being released. So when going down the group, you can see that it become less exothermic. Right? Okay, from this situation, you can see that when the daughter want to come back home, okay, when is a strong attraction with her mother, so it will back home happily. But when they have weak attraction between mother and the daughter, so this daughter cannot come back home happily because it's some boundary, some gap between them. Okay, refer to the electron affinity value. You can see that when going down the group, okay, the energy is become less exothermic, less negative. Okay, so this analogy is only applied for chlorine, bromine, and iodine, which is when going down the group, the attraction force become weaker, and the halogen generally decreases down the group, which is become less exothermic, okay, when going down the group. But okay, if you can see that there some exceptional for fluorine and chlorine here, because if you can see that in formation of fluoride ion, okay, electron affinity of fluorine is more exothermic compared to chlorine. Okay, why this happen? Okay, why? Okay, this happen. Okay, if you refer to the analogy, if you can see about the fluorine, fluorine is the smallest atom of halogen. If you can see that around the valence electron of fluorine, it consists of 7 electron, which is if fluorine atom is already crowded with electron, which is already have another daughter with near to the mother. So that's why when we have one electron to be added, they have some repulsion occur here. Okay, because one is electron and the outer electron, okay, so this is already negative, is also negative. So some repulsion occur when the added electron want to enter the fluorine atom. So this cause the energy become less exothermic, okay, compared to fluorine. So because of the smaller size of fluorine, it have the crowded of electron nearby the nucleus. So it's make the attraction force become less exothermic because of the repulsion. Okay, hence this repulsion weaken the attraction for the incoming, for the added electron, and so it's lessen the electron affinity. So that's why electron affinity of fluorine, okay, become lower. Okay, so now we can plot the graph. We plot the graph of electron affinity. Electron affinity, which is kilojoule per mole, and is negative, because the value is negative. So we can plot that fluorine here, chlorine here, okay, and then bromine and iodine. So this is the graph for electron affinity when going down the group 17. The third physical properties is a bond energy. Alright, let's define the bond energy first. Okay, bond energy is a heat energy required to break 1 mole of covalent bond under standard condition. So the keyword here is a break. Okay, break the covalent bond. So alright, so refer to the halogen, that the stronger the bond. Okay, so the stronger the bond, right? The stronger the bond, alright. Okay, the higher the bond energy. Okay, which is hard to be break, right? Okay, if you can see that when going down the group, alright, the size become increasing. Hence, okay, the covalent bond, okay, the covalent bond, right, in molecule is become longer when going down the group. If you can see for iodine have a larger size, right? So this is the larger, okay, larger size. So hence make the bond become weaker. So it have weaker bond. So how about the bond energy? So become decreasing, right? Bond energy become low lah because of the weaker bond. Okay, hence for chlorine it have smaller size. Okay, so it have a shorter bond. Okay, hence it have a higher BE. Alright. Okay, refer to the bond energy. You can see that when going down the group, the bond energy become smaller, alright, because of the larger sizes. Okay, but what happened to the fluorine? Okay, if you can see that chlorine have higher bond energy compared to fluorine, even though the size of fluorine is smallest. Okay, why this is happen? Okay, why this is happen? Okay, if you see the structure of fluorine molecule, okay, it is a very smaller size. Alright, so why FF bond is unexpectedly weak? Because of the small size of fluorine atom, which bring the 3 lone pair for each other, and then because of its smaller size, so they have some repulsion, okay, between the lone pair with another lone pair. So it repulses each other because it's very closer to each other. So what happen is it's higher tendency to leave their atom. So when we want to break the bond of this fluorine molecule. So that's why it have lower bond energy. Okay, this strong repulsion between the lone pair of electrons so weaken the FF bond, so make it easier to break. Okay, because it's become weakened, so that's why bond energy become lower than chlorine. Okay, it's smaller than chlorine.